volcanologists for a long time have argued that the volcano must have been the cause of the Permian extinction and environmental consequences resulting from this massive volcanic eruption. The oceanographers, the paleoceanographers have been looking at the ocean and they see an anoxic ocean, they see evidence for hydrogen sulfide. That must have been the cause. What we're trying to do actually with our computer models is to bring this all together, to synthesize these into a consistent story of environmental change. And remember, this is the, perhaps the singular event in Earth history. This set the stage in some regards for the evolution of the dinosaurs. This is just before the dinosaurs. And perhaps the biotic change that happened at this time allowed the dinosaurs to take over during the ensuing Mesozoic. And then the asteroid hits, wipes out the dinosaurs, and mammals evolve. And so there are these events in Earth history that seem to be critical to the path of evolution. So it's an important question, and a lot of people are working on it, and they're working on it from their own specialties and their own perspectives. One of the things that we do as geologists is look for modern analogs, places that we can go today that we think are like what the environment we're studying in the ancient rock record was like back then. And so our interest is in, of course, these hydrogen sulfide rich marine environments. And the most obvious place one could go to study that in the modern world is the Black Sea, but that's very inaccessible. Fortunately, here at Penn State, we have a lake nearby. It's actually near Syracuse, New York, but it's a lake that we think is much like what the Permian Ocean was like back then. It has a layer at the top of the lake that's well mixed and oxygenated, and in fact, people swim there and fish there. It's a state park. But lurking down below this upper 60 feet of well-oxygenated water is a poisonous mixture of this hydrogen sulfide-rich water. And so we've been going there. We study this by going scuba diving. So we have divers who dive down into this environment, myself included, collecting samples, not just of the water, but of the organisms that live right at this interface between oxygen-rich water and hydrogen sulfide-rich water below. So we dive right to this interface. We don't spend much time below it because it's poisonous, and prolonged exposure to hydrogen sulfide-rich water can be fatal. So we dive down to this layer, maybe dip down just below to collect some samples very quickly. And we're looking at the chemistry of this water and the organisms that are living there, and we're looking for organisms in particular that produce compounds that we find in the rock record associated with the Permian mass extinction. So it turns out that organisms that live right at this interface between poisonous and non-poisonous water produce compounds that are preserved in sedimentary rocks for up to billions of years. And so we're looking at these modern organisms, we're extracting these chemical compounds from them, we're analyzing them, and then we're comparing them as a fingerprint, as a sort of a chemical fossil of what was living in the ocean at the time. These organisms are bacteria. They don't leave fossils like we're used to thinking, shells or bones. What they leave are distinctive organic compounds that we're trying to relate from the living organism to these ancient fossils. And once we can do that, and we can look at their distribution in these modern environments, then we'll have a much better picture of the conditions in which they were thriving in this Permian Ocean. One of the other interesting things about this interval of time is that the oceans became very similar to what we think they were billions of years ago. And so the Permian, 250 million years ago, was a time period in which the oceans were transformed into what we think the oceans were like a billion years ago. And we know that a billion years ago, the types of organisms that thrived in this poisonous, oxygen-free environment generated a type of rock that's known as a stromatolite. And in fact, this is a stromatolite here. It's a layered rock that forms, this is a cross-section through one. If you can imagine what this would look like, it would be like a head of cabbage. And it's layer upon layer upon layer of bacteria that are growing up off the seafloor, forming a mound. It's called a stromatolite, and in this case, this rock's been truncated, so we can see the inner laminations of this. This is formed entirely by bacteria, and it forms in environments today in very extreme environments, but it was much more abundant in the distant geological past, such as in the Precambrian. What we find out is that right after the Permian extinction, stromatolites come back. So there's a reappearance of this very ancient life form, something that we usually associate with the Precambrian, billions of years ago. At the end of the Permian, right after the mass extinction, these bacterial communities come back and thrive. And so this is another piece of evidence that the Permian Ocean became such an inhospitable place for advanced life forms that it reverted back to an earlier state that we think was more associated with the Precambrian, in which bacteria thrived.